In the vast oceans, where waves and currents are constantly moving, one of the most important and popular forms of fishing in the modern world is purse seine fishing. This method is considered to bring high productivity, outstanding economic efficiency, and at the same time demonstrates the most sophisticated technical level and labor organization in the seafood exploitation industry. Purse nets are used to catch fish that live in schools such as tuna, sardines, mackerel, herring, small mackerel, objects that account for a large proportion of global seafood production. Different from traditional fishing methods such as hand line or trawl, purse seine works based on the principle of encircling and closing the school of fish in a giant net. Then tightening the bottom like a drawstring bag. The structure of this type of net includes many complex parts: floating buoys, heavy weights, ropes, lead rings, towing cables and modern hydraulic winch systems. When dropped, the net forms a wall around the fish, preventing them from escaping. The entire process, from detecting the fish, deploying the purse seine, controlling the net, collecting the fish and preserving them, requires close coordination between people. Electronics and mechanical power. Modern purse seine vessels are typically 50 to 100 meters long. Equipped with sonar, radar, GPS and even aircraft or tender boats to find schools of fish from a distance. Hydraulic winches and net reels can pull hundreds of tons of net in a few hours. On deck, sailors work continuously, coordinating the dropping of buoys, tightening lead rings, closing the bottom and scooping up fish. The origins of the purse seine method date back to the 19th century, when fishermen in the Mediterranean and North Atlantic used large nets to encircle schools of herring. The technique later spread globally, especially in the 20th century with the advent of diesel engines and marine electronics. Since 1950, purse seine has become the dominant method for catching skipjack tuna and big-eye tuna, two species that account for the majority of the world's canned tuna production. The efficiency of purse seine fishing comes from its ability to be fast and large-scale. A successful fishing trip can collect hundreds of tons of fish in just a few hours, something that other methods have difficulty matching. However, along with high productivity comes the challenge of resource management and ecological impact. Because if not properly controlled, purse seine can also catch unwanted species, bycatch, such as juvenile fish. Sea turtles or dolphins. In terms of technical structure, commercial purse seine nets are usually 1.000 to 2.000 meters long and 100 to 250 meters high. The upper part is attached to a plastic or light alloy float. The lower part is attached to a lead to keep the net submerged in the water. Along the bottom of the net are hundreds of metal rings connected to a purse line. When the net is closed. The sailor will pull this line with a hydraulic winch to tighten the bottom of the bag, completely trapping the fish inside. From there, the fish are scooped up by a machine net or high-pressure pump and transferred directly to the freezer. One of the important features of this profession is its high level of mechanization and organization. On each seine vessel, there are usually about 20 to 30 crew members, each person in charge of a specific position, the captain in charge. The radar engineer who monitors the fish stall, the sailors in charge of the net winch, the fish processing team, and the preservation department. The speed, skill and synchronization of the entire team directly determine the yield. The leading countries in seine fishing today include Japan, Spain, Korea, Taiwan, the Philippines, and the United States. In the Pacific region alone, thousands of seine vessels operate continuously around warm waters where tuna move with ocean currents. In the Atlantic region, European vessels also deploy similar systems on an equally large scale. A special feature of modern technology is the use of fish carriers to collect products from seine vessels at sea, helping to save time returning to shore. In addition, many vessels also apply FAD technology, fish aggregating devices, artificial buoys with sensors and underwater cameras to attract schools of fish to the area, increasing the probability of catching. However, the use of FADs has caused a lot of controversy because it can change the natural behavior of migratory fish species, making them vulnerable to overexploitation. International organizations such as FAO and ICCAT have issued regulations limiting the number of FADs allowed to be used each year, to ensure the sustainability of the fishery. An inseparable factor in the study of seine fishing is the method of post-harvest preservation. To maintain the quality of tuna or herring at a high level, modern vessels are equipped with blast freezers or brine freezing systems. This freezing process helps the fish retain its meat structure, color and freshness when exported to sashimi or canning factories. Beyond the technical aspect, seine fishing is also a special labor ecosystem, where people are attached to the sea for months at a time. Working amid storms and big waves. Life on board follows the rhythm of the sea. At night is when the radar is active. During the day is the time to collect and preserve fish. Sailors eat, sleep, and work right on deck, amid the roar of the engine and the strong smell of sea salt. Each trip usually lasts from 15 to 45 days, depending on the sea area and the type of fish targeted. From a research perspective, seine fishing represents a natural evolution of human fishing, from manual labor to industrialization, from fishermen's intuition to precise electronic data. Along with this development comes the responsibility of management. how to ensure that fish resources are not exhausted and the marine ecosystem is maintained. Therefore, fisheries research organizations in Japan, the United States, and Norway have invested in many scientific projects to improve net design, reduce bycatch rates, and increase energy efficiency. One example is seine nets using ultra-light and durable nylon materials. Helping ships save up to 15 to 20% fuel. Some ships are also equipped with automatic control systems, allowing calculation of drop angle, encirclement speed, net depth based on actual data in real time. All these advances make seine fishing not only a fishing activity, but also a scientific industry, combining marine technology, aquatic biology, and electromechanical engineering. Each catch is the result of decades of experience, modern positioning technology, and the spirit of conquering the sea. When studying the technique of fishing with seine, it is found that the whole process is a sophisticated chain of operations, requiring almost absolute precision in each operation. A seine is not simply a net dropped into the sea, but a complex technical structure of the fishing system, including materials, mechanical structures, electronic equipment and human control skills. Each component, whether a small buoy or a lead wire, plays an important role in determining the fishing efficiency. The overall structure of a modern commercial seine usually has an average length of 1.200 to 2.00 meters, and a height of 150 to 250 meters. Depending on the target fish species, the body of the net is divided into three basic zones: the floating zone, the intermediate zone, and the submerged zone. In the floating part, the buoy system is densely arranged, usually made of high-strength composite plastic or lightweight aluminum alloy, helping to maintain stable buoyancy even when encountering strong waves. The middle part of the net is the main body, woven with high-tensile nylon or polyethylene fibers. The mesh is designed to the size suitable for the size of the target fish to optimize fish retention performance without damaging the flesh tissue. The bottom of the net is attached with a heavy lead strip linked to hundreds of stainless steel sliding rings. This is the part that determines the ability to tighten the bottom of the net bag. The operating principle of the seine is based on the ring closing mechanism. When the ship drops the net around the school of fish, the locking rope, called the purse line, will pass through the entire lead ring system at the bottom. When the net needs to be closed, the hydraulic winch pulls this rope, causing the bottom of the net to tighten similar to the mouth of the bag being pulled tight. This is the most important step in the entire operation process. If the timing of closing the net is incorrect or the locking rope is jammed, the fish can escape, causing the entire fishing trip to fail. On deck, mechanical equipment plays a central role in controlling this huge volume of net. The power Power block system, a large grooved net reel, mounted on a hydraulic crane, is designed to roll the net up layer by layer, reducing the load on the sailors. The power block is usually made of aluminum or composite, with a diameter of 1.5 to 2 meters, operated by a high-power hydraulic motor. When the power block is operating, a group of sailors adjusts the rotation speed, while another group arranges the net evenly in the hold to avoid tangles. On large ships, this entire system is monitored via an electronic control panel with a force sensor, displaying the pulling force and rolling speed in real time. In addition to the power block, the purse line winch is an indispensable part. It consists of a large diameter steel reel, capable of withstanding a load of several dozen tons. This winch is usually located behind the ship, controlled by a precise hydraulic valve. Allowing the operator to adjust the pulling force to close the net without breaking the line or distorting the lead ring. On Japanese or Spanish ships, this winch is also equipped with an automatic braking system and a tension sensor, which helps to precisely control the process of retracting the locking rope. Before dropping the net, the captain must accurately determine the location of the fish school using a 360-degree sonar system. This sonar emits an audio signal and receives reflections from the fish school, indicating the density, size and direction of movement. The data is displayed directly on the radar screen, allowing the operator to estimate the size of the fish school and determine the direction of the net. A small deviation in the angle of release can cause the net to not close completely or the fish to be pushed out of the enclosure. When starting to drop the net, a small auxiliary boat, skiff, is lowered to pull the head of the net in a circle around the school of fish. The speed of the boat must be adjusted to the current and wind direction to ensure a uniform net shape. Meanwhile, the mothership moves in the opposite direction of the boat to maintain tension in the net. When the circle is closed, the top and bottom of the net are connected, and the crew begins the pursing process, pulling the bottom rope to close the net mouth. This process takes place in harsh field conditions, under the pressure of waves and the weight of the net. The locking rope must withstand extremely high tension. Therefore, designers often use steel-coated polyester rope to increase the load-bearing capacity. On board, a team of hydraulic engineers continuously monitor the pressure parameters on the oil pipes to ensure the system is not overloaded. When the net is completely closed, the school of fish is forced to the center of the net bag. At this time, the sonar system and underwater camera are activated to assess the density of fish in the enclosure. Based on that, the captain decides when to start collecting the fish. With modern ships, fish are no longer scooped up manually but use high-pressure vacuum pumps, vacuum fish pumps. The pump tube has a diameter of 30 to 50 centimeters, pumping capacity up to 250 to 300 tons of fish per hour. Fish are sucked directly from the mesh bag through the pipe, transferred to the cold storage compartment without damaging the fish body. In tuna fishing vessels, the preservation system often uses brine freezing tanks. The seawater is cooled with ammonia or freon, kept at a temperature of about -35 degrees Celsius to -40 degrees Celsius. When the fish is put into the tank, this temperature quickly freezes the outer tissue, preserving the muscle structure and limiting the oxidation process. For sashimi tuna, the blast freezer method is applied. A cold air stream of -60 degrees Celsius is blown directly onto the fish within 30 minutes after harvest. Ensuring the natural red color and intact freshness. All operations on board are carried out according to standard operating procedures, SOP. Each crew member is trained in their own techniques: the sonar operator, the power block operator, the winch engineer, the fish processing team, and the quality control team. During operation, all data, from catch coordinates, drop times, fish weight, to storage temperatures, are recorded in an electronic logbook for reporting to international fisheries management bodies such as WCPFC or ICCAT. Another important technical factor is fuel efficiency. Since purse seiners often operate in distant waters, fuel optimization is vital. Norwegian and Spanish studies have shown that replacing the net material with high-density polyethylene, HDPE, reduces water resistance by up to 12%. While installing variable pitch propellers and flow sensors reduces fuel consumption by up to 20%. These improvements not only improve economic efficiency but also reduce CO2 emissions, a factor that is particularly important in the European Union's fishing carbon reduction programs. In real-world conditions, human skills still play a central role. The captain must understand the movement patterns of the target fish. Tuna tend to congregate around floating objects or shad. Herring tend to move against the wind, while sardines float near the surface at dawn. The timing of the drop is often based on years of experience. Many captains have the ability to read the sea based on watercolor, wave direction, and seabird activity, skills that modern machinery has not yet fully replaced. After the fish are collected, the remaining net is cleaned with a high-pressure hose, inspected for damage, and rearranged in preparation for the next drop. Regular maintenance of the lead rings and locking ropes is considered mandatory, as a single lead ring that is rusted or broken can affect the entire bottom closing process. Onshore net repair workshops often use large industrial sewing machines and synthetic materials to patch the net, ensuring uniformity in tension and length. In fisheries research, one of the most important factors is the catch per unit effort, CPUE. This is an index reflecting the productivity of fishing per unit of time or fuel. With modern purse seine vessels, the average CPUE is 40 to 60 tons of fish per day, dozens of times higher than that of traditional longline or trawl vessels. However, this index also depends on the fishing area, hydrological conditions, and operating skills. Modern technical research also focuses on reducing the yield of non-target fish, bycatch mitigation. By changing the mesh size at the bottom or adjusting the closing speed of the net. people can significantly reduce the amount of juvenile fish and non-target organisms caught by mistake. Some projects have also tested nets with the ability to selectively open, selective release net, in which the escape hatches automatically open when detecting fish under the standard size. Shipboard electronic systems are also becoming increasingly intelligent. New generation sonar can identify fish density by species based on characteristic reflection frequencies. Underwater cameras transmit data directly to the deck, helping captains decide whether to cast nets or not. Combining these data creates a digital fishing ground map, a strategic analysis tool used in modern fisheries management research. From a scientific and technical perspective, seine is not only a fishing tool, but also a platform for marine technology research. From the design of ultra-light net materials, precision hydraulic control systems, to the application of artificial intelligence in detecting fish schools, all reflect the continuous development of the global seafood industry.